Good morning, class. Good morning, class. So we'll be starting today with capacitors and dielectrics. And as we know, as time goes on, the projector will go up, followed by the microphone. So let's get started and do what we have to do. So when we talk about a capacitor, from the name, it's a device that has the capacity to store electric charges. So there are different devices at home that contain capacitors. When the usual power outage occurs, you will notice that the bulbs will go off, but some appliances like the TV decoder, some bulbs will still spend about a second or two before they go off. Capacitors are responsible for ensuring that those bulbs light up for a few more seconds before they actually go off. I can relate a rechargeable battery to also be a capacitor, because a capacitor can store charge. So you charge it by storing charges, electric charges, and it discharges by performing work when the electrons or electric current flow out of the capacitor, out of the device. So when we say dielectrics, we are only talking about insulators. So there are different types of capacitors. We have ceramic, and we have electrolytic capacitors. The electrolytic capacitors can be related to your batteries that operate considering chemistry. But there is another type of capacitor that is not concerned with chemistry. It's concerned with pure physics. And that's the ceramic capacitor. And the basic of this type of capacitor is you to imagine two parallel conducting plates. Two parallel conducting plates. So if you think about a plate, there is not a technical term. You can think about your stainless plate that are conductors that are flat, parallel, two parallel conducting plates. So when you think about the figure, so when we have, oh, come on, go back. So when this is a plate, oh no, this is a plate, you can see two parallel lines, right? They are very straight. Two parallel conducting plates. They can store charges. They have the capacity to store charges. And how do they store the charges? How do we store charge? We charge the capacitor for it to store charges. These two plates can be connected to a voltage supply, can be connected to a supply that will create a potential difference between the plates. So when these two plates are connected across a potential difference V against a cell of potential difference V, then easily we should know that this capacitor will store charges, and the charge that it will store would have a certain quantity. It will store a certain amount of charge, and the charge it will store is Q. To store charge Q when it is connected across potential difference V. So there is now a constant, which is the capacitance. So capacitance tells us it's a measure of how, let's say, how efficient the capacitor is, how its capacity to store charges is C. And it's called capacitance. And the unit is farad. So farad is the unit of capacitance, and is defined as Q over V. So that is the ratio of the charge stored to the potential difference between the plates. So for any two parallel plates, the charge that will be stored depends on the potential difference across the plates. The charge that will be stored in this capacitor. This is the schematic representation for capacitor. When you draw a capacitor, this is how we represent it. For electrolytic capacitor is of this form. Okay, let me draw it. So the curved part is negative, the straight part is positive. And the electrolytic capacitors, like you would expect, it has positive and negative terminals, unlike the parallel plate capacitors you are talking about, which, fine, one is positively charged, the other is negatively charged, but you can turn it around and use it the other way as you like. So let's go back to the basics, which is for a parallel plate capacitor. For a parallel plate capacitor, it will store a charge Q if a certain potential difference V is set across it. So what that means is that if you increase the potential difference across the plates, the charge Q that will be stored will be increased. And when you reduce the potential difference across the plate, the charge Q that will be stored will reduce. So for different capacitors, we have different C's, which is the ratio of the charge they can store to the potential difference across their plates. The charge. So for a capacitor that stores a charge of 1 coulomb, when it is set across 1 volt, such capacitor can be said to have a capacitance of 1 farad. So that's about the relationship between capacitance, charge stored, and the potential difference across the capacitor. But there is still some other things that defines these capacitors. For a parallel plate capacitor, when the area of the plates, when the area of the parallel plates, when they increase, the capacitance will increase. So when you put 2 plates in parallel, like this, the larger the plates, the larger its capacity to store charges. The larger the plates, the larger the capacitors. So I don't need to tell you the smaller the number. So there is also another variable, which is the closer the plates, the larger the capacitance. So when you begin to bring the 2 plates closer, their capacity to store charges will increase. When you begin to bring them closer and closer and closer, it will store more charge Q. So the closer, the higher. So yeah, on the slide, we talk about area A and distance D. So when area A, the larger the base, the capacitance, and the closer the base, that is the smaller the distance of separation, the higher the capacitance. So there is still also another variable to think of, because when we talk about the parallel plates, in between the parallel plates, we can just assume it's containing air, just containing fresh air. But what happens when you replace that fresh air with a dielectric, with an insulator? What happens when you just slide in an insulator? You have 2 parallel plates. It's storing charges, but you just take, what's an example of an insulator? Just take a car, put it between the parallel plates. The capacitance will change. In short, the capacitance will increase. It will store more charges because you have put in dielectrics. And the change depends on the property of that dielectric. We have what we call dielectric constants, which is directly connected to the permittivity of the material. You define permittivity of free space to be 8.85 times 10 to the power minus 12 farad per meter. But we should now think about the permittivity for different materials. So if you are putting oil, if you are putting glass, if you are putting different dielectric materials, different insulators have their dielectric constants, and these constants affect the capacitance of the capacitor. So if it is nylon, whatever you have put, you have adjusted the property of that capacitor, and you have changed the property, and the charge stored per volts will change. So this is one plate, this is another plate. We've connected them to a potential difference power supply. So this is now at higher potential, the lower plate is at lower potential. And we would expect the electric grid lines to point from the positive plate to the negative. So that's why we have the lines pointing downwards. So we should have come across this expression before, where we have said E is equal to V over D, have we? So anyway, we should come across E equal to V over D from the definition of electric field strength and the definition of potential. You will notice that the only difference is a certain R somewhere and R squared in the other end. So doing that, it's easy for us to say that V over D equal to E. And I think we worked on one example like that has to do with distance, electric field, and we got out the potential also. So the summary of this is that V here is the potential difference between the plates, and that is VA minus VB. So when we know the potential difference between the plates divided by the distance, then we can talk about the electric field intensity. And also, we should also recall what we spoke about when we were talking about charge distribution on a continuous surface, where we're on a continuous continuous charge distribution rather. And when we spoke about continuous charge distribution on a surface, we defined this sigma to be equal to the charge per unit area. So coming back to electric field strength, we can define it as a function of the charge and area. So E will now be defined as 1 over epsilon times Q over A. Okay, I'm thinking of how to make that simpler. We know the electric field to be equal to Q over 4 pi epsilon naught R squared. 4 pi R squared is the surface area of a sphere. So we can replace 4 pi R squared with A. We can replace 4 pi R squared with A. Then doing that, E will reduce, when we replace 4 pi R squared with A, then E will reduce to Q over epsilon A. And in this case, we have replaced epsilon naught with epsilon because it is not compulsory that in between the plates, we are having free space. It can be any dielectric. So the permittivity of that dielectric is why we have put epsilon, so that to be more general. So I think that's the only strange thing we should have there. Is there anything else? No. So C is equal to, okay, like a simple way to remember this is to say that the capacitance of a capacitor is directly proportional to the area and inversely proportional to the area of the plates, and inversely proportional to the distance of separation between the plates. And when we introduce a constant of proportionality, it becomes C equal to, in this case, our constant is epsilon A over D. So that's why we have all this. And that does not change the fact that C is still Q over V. You can see. That's why physics is interesting. The equations don't contradict themselves. Is there any problem? Okay. Yes, the last one. The last one is, okay, epsilon there is the permittivity of the material. Epsilon naught is the permittivity of free space that we have seen earlier, while epsilon r is relative permittivity. So that is unitless. So it's just, so when you know relative permittivity, then you should know the permittivity of that material. So if you have a problem you want to solve, and you don't have information on the permittivity of that material, but you know that of its relative permittivity, you can just multiply it with that of free space, and you do. What's it? Relative density. Yes, thank you. Yes, thank you. So, like you rightly said, when we are talking about all this your density bottle, like when we say relative density, it's also density of a material over a standard, which is density of water. And in this case, the standard here is free space, and that is epsilon naught. I'll read all these stories. So when we have two parallel plates and a voltage is set up between them, just like we had here, a voltage is set up between these two plates. When we insert a dielectric material in between this separation, electric field will also be set up in that insulator. The insulator, just like materials, have protons, have electrons. When you slide in the insulator, the dielectric, in between the parallel plates, you would expect the electrons to move towards the positive plates, right? Electrons, they are negatively charged. You would expect them to drift towards the positive plate of this field of the positive place of this capacitor. So let's move on. Let's move on. Yeah, we need something to come back with. Okay, so I think it's better I have something drawn here. So these are two plates. This is positive, and this is negative, and the field lines are pointing downwards as expected. But now we have a situation where an insulator, a dielectric, is inserted in between the plates. You will expect the positive charges to, you will expect the negative charges to move upwards, making the base of that blue insulator to be relatively positive, because the electrons would have moved from the base upwards towards the positive plates. And when that happens, that means we should have another field lines. Okay, sorry. This is, so the next, let me get blue first. So we would expect electrons to drift upwards, leaving the base of that insulator to be positively charged. When this happens, we should also expect another electric field to be set up in that insulator. Because if you look at that insulator, we have a positive side and the negative side. Now, forget about the parallel plates. Look at the insulator. It's having a positive part at the base and a negative part upwards. Then you should expect electric field to be set up. And in what direction? In opposite that color yellow. So that is what you should expect. So now let's go through the equations and the stories and see what we got. So polarized atoms will tend to align to the direction of electric field. That's what I've just said. This causes the end of the surface of the dielectric medium to become charged. The second field is set up in the dielectric medium due to charges on the polarized atoms. That's what we just said. The arrows pointing downwards. So the diagram I've just drawn, this diagram is just like what you have here originally. So the arrows pointing downwards are electric field lines due to the external field E, that is due to the voltage source connected to the capacitor. So the arrows pointing downwards, you can see some arrows are pointing downwards and they are labeled E. The arrows pointing downwards are due to the external field connected across plates A and B, while the ones pointing upwards are the field lines due to the polarized atom within the field. So if you look closely, you will notice that some lines are also pointing upwards and they are labeled as E subscript delta. So the E subscript delta are the electric field within the insulator, set up within the insulator. Then the problem before us is, what is the relationship between the electric field set up within the insulator and the electric field that was applied externally? And equation 5 shows that it's a direct relationship. The electric field E chronicle delta is equal to E. It's directly proportional to E. And as usual, we introduce a constant of proportionality, beta. So beta is the constant of proportionality, and we have equation 6. So the total E is that we add E to E delta. We add the external field to the field created in the insulator. And because the directions are opposite, that's why the addition, we are having a minus sign in the addition. So to add them up, we are having E, which is the external field, plus E delta. But because the direction is opposite, that is why we have a minus sign. We already established a relationship between E delta and E, which is that is E delta is equal to beta E. Then we can replace this E delta with beta E. And we have this expression, which we can simplify further to be E product of E and 1 minus beta. So beta is a constant that measures the extent of polarization. So if the changes from 0 to 1, and it tells us the extent of polarization. So, and it's also the extent of polarization depends on the dielectric nature of the insulator. So now if we imagine two identical parallel plates, P and T, this is P. Come on. Set parallel. P and T. Oh, we said identical. So they're identical because they have the same area, the same distance of separation, and the same dielectric in between them. So the electric field in between EP, in between the electric field set up in P is the potential difference across the plates divided by the distance of separation. Similarly, ET, which is the electric field set up in between the plates in capacitor T, is the potential difference across it divided by D. So you can see that D's are the same here because they are identical. The only thing that can be strange here is the potential difference across it. As long as we say they are identical, D, the distance of separation in P is equal to the distance of separation in T. So in the absence of dielectric, we would expect, so when, sorry, let's start from here. When VP and VT are potential difference and D is the distance of separation between the plates, in the absence of dielectrics, then EP is equal to ET. So when the dielectric is introduced to capacitor T, so remember this is P and this is T. So when we insert a dielectric into capacitor T, the electric field intensities in P and T are related by this expression. And since E is equal to V over D, then we can also have expression 8. ET is simply saying VT over D, which we have defined upward here. We've defined ET to be VT over D, which we have here. And EP can be obtained from the expression 7. So, in order not to waste our time, I would try to make sure the slides are put on LMS today. And the previous lectures that I was able to record, I've put them on YouTube. So for those that missed the class or want to refresh, like the one we did last class, there is nothing to get about that one. So, but today's one is currently ongoing. It's possible I have today's one and also put it on YouTube. So if you want to get it on YouTube, you just search with my name. So when you get to YouTube and search with my name, you get to my channel and you can watch. I think you can download as well. So let's move on. So materials will be perfectly polarized when beta is equal to 1. When we look at this expression, when beta is equal to 1, that means that the field set up by the external potential difference will be equal to the field setup in between the insulator. That will mean that E will be equal to E delta. And when E is equal to E delta, and they are pointing in opposite direction, then what you'll have will be 0. So there will be no, the total field there will be 0, which will be like a waste of resources. So let's move on. So materials that cannot be polarized will have beta equal to 0. And when beta is equal to 0, sorry, I think so when beta is equal to 0, so you can also put 0 here, and you see the relationship. So when the materials cannot be polarized and they have beta equal to 0, then that means that the relative permittivity will be equal to 1. It will look as if you have not put anything there at all. It will look as if you have not put anything there at all. So when we were talking about the parallel plate capacitors, that as the distance of separation is reducing, the capacitance increases. When you continue to reduce and reduce until D becomes 0, until the two plates touches, then it is no longer a capacitor. Then it can be regarded as just a conductor. So for you to have a capacitor, there must be separation between the conducting plates, and the smaller, the higher the capacitance. So like you said, that capacitor, they have the capacity to store electric charges. Then at this point, we are going to quantify the energy that is being stored. They store, excuse me, they store electric charges in the form of electrical energy, and that electrical energy is what we are interested in on this page. So the potential energy in electrostatics, we have known this. This is not strange, right? To say that E is equal to QV, right? So, and sorry, not E, I mean W equal to QV. W here is work done, right? And work and energy are like neighbors. Or let me say they are relatives. So the energy stored is a charge in potential energy due to the two plates. So the energy stored, now we have two parallel plates. We assume this to be at 0 volts and this to be at a certain V volts. So an easy way to quantify that is to now say that what is the average charge stored? So we start by saying half 0 plus Q. So just like we're trying to find the average, half 0 plus Q times VA plus half 0 minus Q times VB. And when you simplify that, you'll be having half Q VA minus VB. So VA minus VB can be reduced to mean ordinary V. So that will say something like half QV. So V is the potential difference, which is the potential at A minus potential at B. That is VA minus VB. And the energy stored is half QV. So half QV can be expressed in some other ways, like we have seen in secondary school, to be half Q square over C. You can say this is the only formula I have in my head. It says Q equal to CV. This is all I have. Every other thing, I derive them from this whenever I need them. So, and the energy stored in a capacitor, the only formula I have in my head is this half CV squared. The others, I derive them on the spot. When you know half CV squared to be the energy stored, and you are in a scenario where you don't have C, then you can easily replace the C here with Q over V. And when you do that, you would have half QV. When you don't have V, you can replace the V there with Q over C. And you'd have half Q squared over C. So the work done in displacing a certain charge, delta Q, the work done in displacing a certain charge, delta Q, is still this QV. So it's just like we have now tried to put them in a more scientific form to say that the work done, that is the change in work, we now put in, will be equal to the Q times P. Like the total work done is we integrate. So when we agree that also product of the change in charge and potential, then we should easily come and say that when we integrate both sides, we should have W equal to QV. But we are not just integrating this side anyhow, we are integrating from 0 to Q. So when you even do that, no matter how you do it, you'll still end up having our half CV square, half QV, half Q square over C. So this is an example which is already solved. And it's saying that a parallel plate capacitor with dimensions of 1 meter long. So imagine the parallel plates like this, 1 meter long, 1 millimeter wide. So 1 meter to 1 millimeter, that should be like, this size is like 1 and this is like 1,000. So 1 meter long to 1 millimeter wide are insulated from each other. So there are 2 of these plates. Another one is up here, the same dimension, 1,000 millimeter by 1 millimeter. So it's easy for you to calculate their area. But I advise you work in meter and not in millimeter. So when you calculate the area in meter squared, then you can say you have the area A. So and the information continues to tell us that they are insulated from each other by a cushion of air. And the cushion of air, the distance of separation between them is 0.1 millimeter. So since the distance of separation is 0.1 millimeter, then that D is equal to 0.1 times 10 to the minus 3 meter. And now it is connected to a terminal. of 1 volt. So what is the energy stored? So we know the area. A, we know the distance of separation. B, we know the permittivity since it's cushion of air. That's permittivity of air, which is approximately permittivity of free space. Then we can use 8.85 times 10 square minus 12 per meter. By doing that, we obtain the capacitance of that capacitor. If we know the area of the plates, the distance of their separation, the permittivity of the dielectric, then we know the capacitance of that capacitor. And when we know the capacitance, it's easy for us to obtain energy stored, since we know the potential difference across the plates by using series code. So I suggest you practice. And I should mention that in physics, we practice. If you sit down and you follow the slides, you will enjoy following and following. But when you are left all alone for the first time, you have a high probability to get stuck. So it's good you get stuck in the library, in the toilet. Don't get stuck in the exam, because that's a primary assignment. So we have capacitors. We represent them with their schematic symbols, that is 2 parallel plates. We can connect them in series and parallel. Just like you must have come across, oh, I don't know if you were born when we still use Tiger batteries. Okay. Once upon a time, we used to use Tiger batteries. We put them in touch. We don't recharge them, but we connect them in series. So that's the type of connection we have here. And nowadays, we have inverters, where you have a single inverter and you are connecting it to like 4 batteries, when each of them is rated 12 volts. And let's say your inverter is rated also 12 volts, then you should connect all the batteries in parallel. When what we mean by series is that the positive of one is connected to the negative of the other, and they form a straight channel. While in parallel, all the positives are connected to a common conductor, while the negative terminals are connected to also a common conductor. So let's try and understand what is happening here. What's happening here is that a certain potential difference V has been set across 1, 2, 3, 4 capacitors. And each of them now have different voltage set across them. This is now V1. For C2, we are having V2. Across C3, we are having V3. And across CK, we are having VK. And the sum of these voltages, that is V1 plus V2 plus V3, and all to get to VK, will add up to give you potential difference V across them. For this, I will get start to say that the potential difference across all of the capacitors in series is equal to the sum of the individual potential differences across each of the capacitors. And we know a standby rule that says that Q is equal, V is equal to Q over C. So by that, we can replace all the V's with Q over C. In short, this first V here is also Q over over C total. So when there is also another property we should note, which is that the Q, the charge stored in C1 is equal to the charge stored in C2, is equal to the charge stored in C3. So the charge stored in capacitors in series are equal. The charge stored in capacitors in series are equal. The charge stored in capacitors in series are equal. So when we know that, then Q can be the same all through. Then when we come to this particular equation, Q is common. We bring out Q multiplying 1 over each of the capacitance. And at the long run, we'll be having 1 over C total being equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C4, so we get there. Whereas in parallel connection, you have to now imagine this to be turning this way. They are standing that way to conserve space. I should have put them this way. So as you say, this is C1, C2, C3, and we connect them across a certain voltage V. In this type of connection, the voltage across V1, the voltage across C1 is equal to the voltage across C2, is equal to the voltage across C3, is equal to the voltage across C4, is equal to the voltage across C5, is equal to the voltage across. I get quiet so that they will not say this is what I just can't say once. But I can continue, but I don't want to bore you. So we should know that V is the same for components that are in parallel. V is the same, that is the potential difference is the same. And what is this potential difference again? The potential difference is related, is still the same potential difference in Q over C. But before we go there, in parallel connection, unlike series, the charge stored in Q or in C1 is not necessarily going to be the charge stored in C2. So Q in the individual capacitors vary. The Q in the individual capacitors depend on the capacitance of these capacitors. So since we know that, so that's the origin of this expression that says Q equal to Q1 plus Q2 plus Q3 down to QK. And we know that Q is equal to CV. Then this Q is the total charge Q times the same potential V is equal to Q1 C1V, Q2 C2V. Remember that V is the same for all of them. Since V is the same for all of them, that is why V is remaining constant over here. So at the end of this expansion, we can divide all through with with V. I'll divide all through with V. They will be left with C total equal to C1 plus C2 all to CK. So I think this is a convenient place to stop. So we should just put at the back of our minds that for a series connection, the potential difference across each of the capacitors add up to be the potential